Hello viewers, here is Dr. Mala Das Sharma and I welcome you all to my tiny YouTube channel MALACHEMPHILIC. Today I am going to start video number 121, which is the episode number 61 of Chemical Thermodynamics, where the topic is Gibbs equations for non-equilibrium system. So let's start. See, before going to the actual topic, let's discuss about the thermodynamic equilibrium. What we understand about this thermodynamic equilibrium? Thermodynamic equilibrium means any system is said to be in equilibrium when its observable properties, say temperature, pressure, etc., will not change with time. And the different condition for thermodynamic equilibrium. Number 1, thermal equilibrium, where no heat exchange occurs with the surroundings, so temperature remains constant in all the parts of the system. Okay. Then mechanical equilibrium. Mechanical equilibrium means pressure remains constant. Then chemical equilibrium. Chemical equilibrium means considering chemical reaction. When the equilibrium is reached, then we know rate of the forward reaction will be equal to rate of the backward reaction. That means this amount or number of moles of the reactants or products will not change with time after reaching the equilibrium. So concentration of the reactants and products do not change with time. Then material equilibrium. Material equilibrium means there will be no exchange of matter with the surroundings. So composition or number of moles of the components will not change with time. That is possible for the closed system. Okay. Now, so Gibbs equation for the closed system where only mechanical work is involved, that we have derived in my earlier video. I'll give the link in the description box. All these equations I have derived there. Okay. So what are these Gibbs equation for this closed system? Okay. Number 1, change in internal energy is equal to TdS minus PdV. Number 2, change in enthalpy dH is equal to TdS plus VdP. Number 3, change in that Helmholtz free energy dA is equal to minus PdV minus SdT. Number 4, change in Gibbs free energy dG is equal to VdP minus SdT. And there I told that these 4 equations are the fundamental thermodynamic equations for a system of constant composition, where composition cannot change. That means closed system. Okay. Now coming to our actual topic, that is Gibbs equation for non-equilibrium system. See, we know that any extensive property, definition of extensive property means the property which depends on the amount of the substance or amount of the matter or number of moles of the substance or components present in the system. So any extensive property depends on the amount. Next, say for open system, now we are considering open system or two or more components. Then open system means they can exchange the matter with the surroundings. So there is a chance of change in the number of moles of various components in the system. When there is a chance of change in the number of moles of the various components in the system, then this extensive properties value also will change. That means in that case, these extensive properties values will not change with the change in temperature and pressure only, but also change with the number of moles. Okay. So in that case, any extensive property is a function of temperature, pressure and number of moles of the different components present in the system. That means For open system, any extensive property is the function of temperature, pressure and number of moles. Okay. Say, if I take any extensive property, say I am taking this Gibbs free energy. Okay. That is the extensive property. So, this Gibbs free energy, in that case, it will be the function of temperature, pressure and also the number of moles of different components. Okay, say Nj. Okay, now if I take the complete derivative of this equation, then dg will be is equal to dou g by dou T at constant pressure and the composition, that is total composition, number of moles of all the components. Say here I am writing C, my N1 plus N2 plus dot dot, that is equal to N. Okay, total composition, then dt plus dou G by dou P at constant temperature and the composition, then dP plus dou G by dou N1 at constant temperature, pressure and composition of other component at dN1 plus dot dot dot, I can write dou G by dou Ni, that is ith component, then at constant temperature, pressure, then N1, N2 and other things up to Nj, and J not is equal to I, because I have taken ith component. So here it is then dNi. Okay. Now we know that dg is equal to VdP minus SdT. Okay. Then dou G by dou P at constant temperature, that will be is equal to V. Okay. And again, already we derived all these things earlier. Dou G by dou T at constant pressure, that will be is equal to minus S. And we know that this dou G by dou Ni at constant temperature, pressure and composition of other components, and J naught is equal to I. This is equal to the chemical potential of the ith component. All these things we know. Change of Gibbs free energy with per mole change of the number of moles of component I, per mole change of the component I at constant temperature, pressure and the composition of other component, that is the chemical potential of the ith component. So if I put all these things in this equation, then what it will come? dg is equal to VdP minus SdT plus summation of mu I, because all these terms together I am writing summation of mu I dNi, where I is equal to your 1 to j. Okay, and this is, say this is the equation number 1. Right. So my equation number 1, which is the key equation of chemical thermodynamics, and this equation, it is for one phase system. So I'll write here this equation for one phase system, that means only one phase is there, homogeneous. Okay, one phase system in thermal and mechanical equilibrium, in thermal and mechanical equilibrium. Equilibrium, I'm writing like this, EQUIM, equilibrium, at PV work only, because earlier also I told you here we are considering only PV work, pressure volume work, PV work only. Okay, this is equation number 1 for open system we have derived. So once again I write here this equation number 1, dG is equal to VdP minus SdT plus summation of I mu I dNi, and I is equal to 1 to J. And this was my equation number 1. And this equation 1 is the key equation of chemical thermodynamics. So, this equation 1 is the key equation of chemical thermodynamics. Okay. And this equation 1 applies to the process in which single phase system, already in earlier I have written earlier slide, single phase, we are considering here only one phase, single phase system, and it is in thermal and mechanical equilibrium but not necessarily in material equilibrium. So this equation, it is not necessarily in material equilibrium. So this equation 1 holds during the irreversible chemical reactions where this number of moles or amount of the reactant and product changes. Okay, with time what happened? Amount of the product increases, right? So irreversible chemical reaction, and during the transport of matter, that means exchange of matter, in case of open system that is possible, exchange of matter with the surroundings means this number of moles of the components will change. So for this equation is applicable. Okay, right. So this equations applicable to the open system. Already for the closed systems, Gibbs equation for the closed system, already as I told you, I have derived in my earlier videos this equation. Now for open system, what it will be? Just I have to add this one related to the number of moles, that is mu I dNi. Okay. Then number 2, dH is equal to TdS plus VdP. Then I have to add this one. Say here I am writing I is equal to 1 to J. Say mu I dNi. Then number 3, here also I have to add summation of mu I dNi. And then number 4, here also I have to add if I consider it for open system. Up to this much it is for closed system where composition remains constant, no exchange of matter with the surrounding. So if I apply it for open system, then we have to add this part, that is related to the number of moles of the components, right? And so This is for all these equations for one phase system, remember, which is in mechanical thermal equilibrium and only pressure volume work. Every time we are taking this condition. So, these equations are extension of Gibbs equation to processes involving exchange of matter with the surroundings or irreversible composition change. Okay, it's a chemical reaction, irreversible composition change. And these are the Gibbs equation for non-equilibrium system. And once again, I'm telling you, this is for one phase, right? So now come. So this equation, so Gibbs equation, if I write, dG is equal to this VdP minus SdT plus summation of mu I dNi, say I is equal to 1 to j. This is for one phase. So this equation for one phase or single phase, or I write properly, this is for single phase. Single phase, say alpha phase. Okay. Then this G alpha, that is the Gibbs energy for alpha phase. See, G alpha, if I write like that, that is the Gibbs energy, means Gibbs free energy for alpha phase. And if I consider G is the Gibbs free energy for the entire phases, that means all the phases of the multiphase system, entire phases of the multiphase system, then what can I write? I can write that is G is equal to summation of G alpha. I can write. Fine. In that case, what I can write? dG is equal to, and also I can write dG. dG is the change of Gibbs free energy of all the phases. So, dG will be is equal to summation of dG for alpha phase, right? Then, my Gibbs equation only for alpha phase I can write like this, that is dG alpha is equal to V alpha dP minus entropy of alpha phase dt plus summation of mu I alpha, then dNi alpha. This is for alpha phase, only alpha phase only. Now for total, that means for all the phases together, if I write, where this dG is the change of free energy for all the phases, then that dG will be is equal to, what it will be is equal to? Summation of V alpha dP, here it is alpha, minus summation of S alpha dt plus summation of alpha, that means for all the phases, summation of I, then mu I alpha and dni alpha. And this is the Gibbs equation for multi-phase system. Okay, open system and multi-phase system. So this is my Gibbs equation for non-equilibrium, I'm writing like this, multi-phase system. Okay. So what we have learned, that whenever the system is open system, then exchange of matter with the surrounding is possible. The number of moles of the different components, if it is a mixture, that will change. There is a chance of change in the number of moles. In that case, extensive property also changes, not only with the change in temperature, pressure, but also with the change in the number of moles. So then we have derived that Gibbs equation for non-equilibrium system or open system. Hope you have understood. Thank you.